Hello everyone. Thank you Fangping for the introduction, motivation, and thank you Fangping for the introduction and motivation. And I will now next explain the next few slides. So starting with application in interdomain routing. So we have already shown the possibility of coordinating knowledge-driven policies from a single central point, but let's now discuss more about more realistic network scenarios, like for example in interdomain routing. So we show an application which we call policy exchange. So before delving into policy exchange, we show a brief picture of what Border Gateway Protocol or BGP is. So we have autonomous systems all across the network, which are smaller networks that are managed by a single enterprise or a single service provider. So these are distinct from each other in that they don't share certain information amongst each other. So BGP is a shortest path routing protocol, and it favors autonomy, that is, it favors the specifications of this individual ASs that exist. So why do we use policy exchange? So why this application? So as I said previously, BGP favors autonomy and policies are made based on local preferences. But this may cause unwanted interaction between these policies. So for example, I show a network which has which has 6 nodes, and there is the node X which has a policy that it says that it requires routes with no more than 3 hops to the destination 1.2.3.4. And there is also another node A which has a policy that says that it balances traffic for its neighbors C and D. So now when X propagates its policy, it says that we can see that it has a valid path XACE that satisfies the policy that it requires not more than 3 hops from X, and it also satisfies our traffic balancing policy at node A. So A can choose the path ACE and X can choose the path XACE. But we also have another path option which is XADBE, which although it satisfies our policy at node A, which is it is balancing the traffic between neighbors C and D, but it does not satisfy our policy requirement at X of the maximum 3 hop count to 1.2.3.4. So if A chooses ADB, then there is a policy requirement mismatch between the two nodes. So we require to make a proper decision, and thus here comes our approach, which we call policy exchange. So how do we do policy exchange using our tool? So we have a node X, as we stated previously, which requires no more than 3 hops to the destination 1.2.3.4. And we have denoted it in terms of our policy table, which has a conditional column which says that Lx should be less than equal to 3. Similarly, we also have our policy table at node A, which has conditional columns for the flags U and V, which state that U can either be equal to 1, when traffic is flowing through C for 1.2.3.4, then it cannot flow through C for traffic 5.6.7.8. So this is how it balances traffic here. So now our policy at node X will propagate to our node A, and we can see that the difference it makes is that the hop count required is now less than equal to 2, because we already accounted for the 1 hop that X takes to visit A. Next, we merge the policies, that is the incoming policy from node X and also the existing traffic balancing policy at node A. And this is how our new policy table will look like. So it will incorporate both our Lx less than equal to 2, and it also has our U equal to 1 or V equal to 1. And here we see that the only line or the only tuple that is not satisfied is our tuple at 1, 2, 3, 4 through our next hop D, because Lx is not less than equal to 2, so it is a contradiction and we get rid of this line. So we have the resulting 3 remaining lines in our policy table now after the merge. So now we have a preliminary prototype which currently uses in-memory implementation in terms of Python lists. We also have real-life applications The first one that I showed already is policy exchange. The other one is BGP simulation, which is mimicking the behavior of the BGP speaker as it receives announcements from the neighbors. So we have used a benchmark of MRT format RouteView BGP data, that is the RIBs and the updates from RouteView to OregonX.net, and we have generated synthetic policies and realistic topologies from this data. Now we move to our performance, which we have counted in terms of the number of policies, and we see that we have a projection, a selection, and a join. The join is that we have shown is between P1, which is policy 1, which is a static route and filter policy, and P3, which is a traffic balance policy. So we see all those three actions that we perform and the time that they take, and we can see that our join, it takes the largest amount of time among all those three. So next we come to scalability, which we discuss the scalability property of the join that we discussed on the previous slide, and we see that for 100 policy sizes and 1000 policy sizes and 10,000 policy sizes, we see an increment in time, but also we see that the majority of this time is required due to our Z3, that is our SMT solver. So SMT solver nearly takes 96% of the total time, and our implementation, we can see, can handle around 10,000 policies in less than equal to 70 minutes, or like around 1 hour, a little more than 1 hour. So we can show more policy examples. For example, we have P1, which is a static route policy, P3, which is a traffic balance policy, P4, which is a filter policy, and we see the total time that they take. And again, we see that the total time is dominated by SMT solver. So we have so P is a primitive that validates a relational policy P. So this is a primitive that validates a relation policy P on a given network state S, and the running time P3 is less than equal to P1 is less than equal to P4, as we can see. So we also see that SMT, as I said, dominates the source of the delay. So we have related works, which is interdomain routing protocols and architectures, for example DBGP and Trotsky, which are partial deployments of the protocols, and they require their coexistence on the global internet in order to function. So we have declarative networking, where we both of us share the database usage in networking, and we introduce and implement, instead of them, we introduce and implement a novel use of conditional tables as well. Thank you. For more information, you can visit HTTP, or for more information, you can visit the website or refer to our paper. Thank you.